Hello everyone, let's begin with the 12th lesson of the Python web series. In this lesson, we will mainly cover scientific computing using Python, focusing on the pertinent libraries. We will begin with some basic concepts of the Python scientific computing, then look specifically at the Numpy, Pandas, and Scipy libraries. Well, we're aware that Python is very suitable for scientific computing. There are several reasons for this. First, Python is a language with a relatively low learning curve. It also has an active community that can provide a wealth of relevant libraries. Furthermore, Python is interpretable and executable, with somewhat simple debugging. Finally, Python has strong versatility, being highly portable and a supportive multilingual integration. What is multilingual integration? For example, we can use Python to call Java and C++ modules. In addition, it supports full-stack development, meaning we can do both front-end and back-end development, as well as algorithm-related work. Therefore, Python is very versatile. Among the Python scientific computing libraries, the de facto standards mainly include Numpy, Pandas, Scipy, Matplot, and so on. We can also take advantage of the machine learning algorithms, such as sklearn, as well as deep learning toolkits, including TensorFlow and PyTorch. The figure on the right lists some scientific computing, including machine learning, libraries in the Python technology stack. The bottom layer is the basic Python packages, including the Python 2 and Python 3 series. Above them, we have ones that performs matrix operation, scientific computing, and machine learning. Our lesson today will mainly focus on the middle two. Matrix operation is mainly done through Numpy. Beyond that, there are the Pandas, Scipy, and Matplot libraries that handle scientific computing. These three packages are higher-level applications developed on top of Numpy. At the top are sklearn, PyTorch, and TensorFlow libraries, all related to machine learning, and developed on top of the scientific computing libraries. Again, our focus will mainly be around what's in the red box. Let's take a look at each in more detail. We begin with Numpy. Numpy is a library mainly for numerical calculations. It is a Python extension library with the capacity of encapsulating and operating on multidimensional arrays. So, what is its main function? It enables calculations such as vector multiplication and addition to be performed on matrices with large data volumes and multidimensional arrays. It also provides a rich library of mathematics functions. We can call these methods directly, without the need to manually implement matrix multiplication operations. What are the characteristics of Numpy? Its main feature is that it has powerful n-dimensional array representation and calculation capacities. Numpy's fast and generalized vectorization, indexing, and propagation functionalities are the de facto standards for array calculations today. Furthermore, it is a tool for numerical calculation. Numpy provides a comprehensive set of mathematical functions, including random number generators, linear algebra calculations, Fourier transforms, and so on. In addition, it is highly adaptive to hardware. We know that when doing scientific computing, we not only can use the CPU as the computing core but also the GPU. Numpy can support a variety of hardware and computing platforms that can perform well in distributed GPU and sparse array computing. Other advantages include its being open source, having a low learning curve, and being highly optimizable. The codebase of Numpy is well-optimized C code, and we know that C has the reputation of having very high execution efficiency. So, while the library benefits from the flexibility of Python and its speed of compilation, it is also able to maintain relatively high computing performance. The figure on the right shows some basic syntax of Numpy. Before we use the scientific library, we first need to import it. We then use the arrange, reshape method, etc. from the library to create multi-dimensional arrays in the shapes and the sizes that we need. We can view the size, dimension, data type of its elements, etc. of a multidimensional array through its attributes. We will cover this in more detail a bit later. Let's now take a look at Pandas. Pandas is mainly a scientific library for data analysis. In Python, Pandas is built based on Numpy's array type, more specifically the multidimensional array type ND array. Its main function is to facilitate data processing and analysis. Pandas is specially designed for processing tables and mixed data. Numpy, on the other hand, is more suitable for processing arrays of uniform numerical data. Let's take a look at the main features of Pandas. The first is its data model. There are mainly two types. One is the single-dimensional series, which we can understand as a vector. The other is a multidimensional data structure represented by data frame. Data frame is encapsulated based on ND array and has a rich numerical analysis toolkit. In addition, the library can be integrated with some distributed computing frameworks, which makes it easy to perform distributed calculations, therefore increasing efficiency. The same three characteristics of being open source, easy to learn, and well-optimized apply to the library as well. The figure on the right shows some Pandas basics. Say we want to use it to create a data frame. Here's the relevant structure. It has several columns A, B, C, D, E, F, G. Each can have a different data type. We can see Pandas can handle mixed data. Having different columns with the different data types make it more of a relational data or data table structure, as we mentioned before. Here's the printout of our defined data frame. We can see that it looks like a relational data table. The first row is the column names A, B, C, D, E, F. Each column corresponds to a value, which is a data type, a numeric type, or a string type. We've now covered some Pandas basics. Let's look at Scipy. Scipy can be said to have a higher level of abstraction. It is a library for scientific computing, which is closer to the advanced mathematics we usually learn, including linear algebra, calculus, and so on. Many mathematical formulas and algorithms are encapsulated with Scipy, which can be called directly. This represents another level of advancement in capacities. So what is Scipy? It is also an extension library based on the Python language. It is based on the basis of Numpy, which provides a wealth of scientific computing functions. I have listed some here, including some optimization methods, linear algebra, integration, interpolation, fitting, special functions, fast Fourier transform, signal processing, image processing, ordinary differential equation solvers, and so on. We can see that it is a very powerful functionality. We can implement these scientific computing functions by calling the corresponding methods in Scipy. What are its main characteristics? As mentioned earlier, it provides a wealth of scientific computing modules, which essentially span the full spectrum of advanced mathematics, including ordinary differential equations, linear algebra, probability, statistics, and so on. At the same time, it also provides some machine learning algorithm modules. So there are some overlaps with libraries that specialize in machine learning algorithms such as sklearn. Don't worry about that for now. We'll dig deeper a little later. The figure on the right shows how we can use Scipy to perform scientific calculations. As we know, we have to first import the modules of these toolkits into the current execution environment. We have now declared a two-dimensional array on which we can calculate some statistics and run some characteristic analysis. Here we've run k-means or clustering algorithm in machine learning. That was a brief intro. Now let's look at the matplotlib library, which is mainly used for data visualization. Why do we need matplotlib? This is because plotting out the original or intermediate result data often helps us better understand them intuitively. Matplotlib is a library of Python-based data visualization tools, which provide static or interactive visualization functions. Through these methods, we can make different charts out of the data. This is the main purpose of matplotlib. It is usually used in combination with Numpy, Pandas, and Scipy, and together closely resembles the capabilities of MATLAB. Let's take a look at the figure on the upper right corner. In this figure, we use Numpy to generate the data first. After the data is generated, we create the plot through matplotlib, including specifying its coordinates, the label and title of its horizontal and vertical axes. the title of the plot, and so on. This is the code and the resulting plot. Representing the data in this manner allows programmers to get a better grasp of the data structure as well as changes in the data. This is the main purpose of matplotlib. Now let's look at the Numpy knowledge system. Numpy's full knowledge system is more extensive than what we have illustrated here. Just imagine more AND nodes. We have selected a few representative points to go over, including ones related to data structure, computational function, linear algebra, as well as I/O operations, which reads and writes data to disk. In data structures, for example, we will introduce multidimensional arrays, array creation, data operations, slice index. For computational functions, we will cover mathematical functions, statistical functions, bit operations, string operations, and so on. In the section on linear algebra, I will explain matrix operations, matrix decomposition, etc. In terms of I/O, I will introduce the loading and writing of text and object data, which is essentially serialized storage and loading of objects in object-oriented programming. Let's begin with data structures. Before delving into the scientific computing libraries, we first need to know their underlying data structure or data model, because all subsequent operations are based on this. For the Numpy library, its core data structure is ND array. So what is ND array? Let's break down its name. ND means multidimensional, and array is an array. You can understand it as a Python list that we explained earlier. N, in this case, can be greater than or equal to 1. This is to say the array can be one-dimensional or multidimensional. If it is two-dimensional, it represents a matrix. If it is an array with more than 2 dimensions, it represents a tensor. These concepts are commonly used in scientific computing and machine learning. NumPy's ND array requires that every element has the same type. It is not like the Pandas data frame we just talked about, which can contain different data types. For NumPy, all elements must be of the same data type. Each element in the ND array has the same storage area in memory. Because each element has the same data type, the size of the storage space open up in the memory is also the same. This means that ND array is more suitable for representing vectors, matrices, and tensors. On the right is an example. Let's take a closer look. First, we import NumPy into the execution environment. Import NumPy as NP, which renames it to NP. We can call some methods through the NP object. We first create an ND array by passing in a list to the NP array method. This list is now a two-dimensional array, which is a list in the traditional sense of the Python language. We print out the NP array object, its type, and its specific value. We can see that its type is np.ndArray, and the printed values is the two-dimensional array 1, 2, 3, 4, 5, 6. In linear algebra, we have the standard matrix form, which is illustrated in the lower right corner. Let's take a look at the ND array data structure or data model and its attributes. When we use NumPy, we often need to know what attributes are included in the ND array object, the dimensions of the array, its shape, and how many elements there are. Because when we are doing scientific computing, after representing the loaded data as an ND array object, we often need to know some of its properties. Some of the commonly used attributes include ndarray.ndim, which expresses the dimension of the data object, shape, which expresses the shape of the object, size indicates how many elements are in the object, dtype indicates the data type of each element. In the example on the right, we have created an ndarray object using np.array, passing in a one-dimensional array, 1, 2, 3 with 3 elements. Now let's take a look at its dimensions. The dimension should be 1 because it is a one-dimensional array. Since it is one-dimensional with 3 elements, its shape is 3, the size is 3. The data type of each element is int64. So these are some of the basic properties of the ND array object, and we can do some scientific computing on it later. There are times when we need to know the number of bytes elements in the object occupy. Let me give an example. When we use deep learning algorithms, we often operate on tensors or high-dimensional arrays. which may be very large, we need to calculate the memory space consumed by the entire model. At this time, we must know the number of bytes occupied by each element. Otherwise, it will cause memory or video memory overflow. We said earlier that all elements of one Numpy object occupy the same number of bytes. We can get that number by using the item size attribute. For example, in the middle figure, the end-array object is still the one shown in the previous slide. When we call its item size attribute through np_array, we can see that the value is 8, which means that each element occupies 8 bits because its data type is int64. Let's look at how we create the ND-array. There are many ways to do this. We'll cover a few of them. The ND-array object can be created with a combination of Python arrays or tuples. But passing in discrete values is not allowed. Let's take a look at the example on the right. In the upper right corner, we have created 3 ND arrays: array 1, array 2, and array 3. For array 1, we passed in a Python list. It is created like this. Well, for array 2, we use a list of tuples. We still use a Python list for array 3, but we specify that its data type is not int, but float 64. Let's see what we get when we print out the array contents. We can see array 1 is like this, and array 2 is like this. Array 3, because we specify that its data type is float, it gets expressed in a decimal form. Let's look at array 4, which is commented out for now. This is not an acceptable method to create an ND array since we cannot directly pass in discrete values. In this case, it will report a type error. We see that the array method only takes 1 to 2 positional arguments, but 4 are given in this case, so we get an error. This is something we want to avoid. Other than auto-assigning the data type of ND array in the creation process, there are other ways to accomplish the same. Numpy supports the creation of ND array objects with special elements. What does this include? Can we create an ND array object with all random number elements within a certain range? We can. Can we create an all0 or an all1 ND array object? These are commonly used in scientific computing. When doing machine learning, oftentimes the model or algorithm calls for parameter initialization to be set as a high-dimensional array of all zeros. We only need to specify the size and then create that array. The figure in the upper right corner illustrates this situation. The first one is np.ones, 2, and 2 is passed in as a parameter. This means that I want to create a 2-element ND array with a size of 1. It is how it is printed. It can also create an ND array object with a size of 2, 3, and all zeros, and print it out like this. There is also a third case when we create random numbers between 0 and 1. Now let's take a look at the parameter description of the special multidimensional array objects. The parameters passed in all represent the shape of multidimensional array. If we pass in a tuple, it can contain 2 or more elements. This represents the shape of the multidimensional array created. If only a single value is passed in, a one-dimensional array is created, and the parameter value represents the number of elements in that array. Let's look at an example. We now need to create an ND array object with dimension 3 and elements that are random numbers between 0 and 1. We can do this with this line of code in the upper right corner, np.random.random. Because its dimension is 3, the parameter tuple contains 3 numbers, 2, 3, 2, which represents the number of elements in each dimension. The random number automatically generates numbers within the range of 0 to 1. After printing, you can see that it is indeed a 3-dimensional ND array object like this. Now that we know how to create ND arrays, let's look at some related operations. First, we'll cover some basic mathematical operations between 2 ND array objects, including addition, subtraction, multiplication, division, and so on. In the figure on the right, we have manually created 2 ND array objects, array 1 and array 2. Array 1 is a 2-dimensional array, and array 2 is a 1-dimensional all1 vector. For array 3, we add 100 to array 1. We can see the resulting values after adding 100 to each element of array 1 become 101, 102, 103, 104. Now we set array 3 equal to 101 plus array 2. Since array 2 is all ones and array 1 is 1, 2, 3, 4. After adding them, the result is 2, 3, 4, 5. In the first case, we can see that we can add a single value to a 2 by 2 ND array. In the second case, the two arrays have different sizes, but we are still able to perform the addition. This is NumPy's broadcast feature. That is, when the shapes of two NumPy objects are different, it will expand the similar-sized ND array object and then do the calculation. If the shapes of two NumPy objects are different, then we look at the dimensions of the trailing edge of the two arrays. What does that mean? That is to the dimension counted from the end. If the axis lengths are the same, or one of the length is 1, we consider this broadcast compatible. Adding, subtracting, or multiplying, etc. can be done by expanding the array. In the previous example, 100 is broadcasted into a 2 by 2 ND array object and added to each element of array 1. In the next example, array 2 in the process of being added to array 1 gets expanded to a 2 by 2 array of 1s when initially it's 2 by 1 and then gets added to array 1. Now we have an idea of how NumPy broadcasting works. Let's look at other NumPy operations. Here we have the aggregation operation. Say we want to find the largest element or the smallest element in an ND array object, or we want to get the sum of all the elements in the ND array, etc. Let's take a look at the figure in the upper right corner. It is the operation to find the maximum value. For our object array 1, its largest element is 4. We can get the maximum value through the array1.max method. That's 4. Here we passed in the access parameter to the max function. What is equal to 0? This means that we want the maximum value of a certain dimension. If the value passed in is 0, it finds the maximum value by column, because 1, 3 is one column, 2, 4 is another column. For the first column, 1, 3, its maximum value is 3. For the second column, the maximum value is 4. If the parameter we passed in is 1, then it finds the maximum value by now, which should return 2, 4. We can see that it is indeed the case here. Now let's look at the sum. We can just call the sum function on this object. The result is 10. Now let's talk about NumPy's slice index. There are scenarios when we want to take a portion of a complete ND array object, often by using a conditional statement to select the appropriate elements. This is where we should use the index functionality of ND array. What are the main types? There is the slicing method and the Boolean method. Let's take a look at the slice index first, which obtains a subset of the original ND array object by slicing the index. For example, in the figure on the right, array 1 is an object like this. What are they hoping to obtain? Well, we want to get all the rows of the array 1 object and the columns between the starting column and the second column. We see that the object only has 2 rows, and we need to get the columns before index 2. Note the column indices start from 0 and are 0, 1, 2. So to obtain the first 2 columns, we will need the 0 and 1 indices. We will observe that the column of the last index is not obtained. The result we get is the subset 1, 2, 4, 5. Now let's take a look at the Boolean index, which obtains a subset when elements satisfy a particular Boolean expression. For example, we want to return all the elements in array 1 that are greater or equal to 3. We pass in the Boolean expression to array 1. If an element satisfies the Boolean expression, it gets returned. For our case, we will get 3, 4, 5, 6. Finally, let's take a look at how to merge 2 ND array objects into one, using the 2 methods hStack and vStack. The parameter passed in is a tuple. The tuple contains several objects you want to merge. This can be 2 or more ND array objects. Here we have 2 objects, array 1 and array 2. Using the hStack method, the merge is horizontal or by row. The result is that the 2 are merged into a single vector. vStack, on the other hand, merges vertically or by column. So in this case, the combined result becomes a 2-dimensional array, 1, 2, 3, 4. Now let's move on to some functions for numerical calculations, including logarithmic, trigonometric, exponential, and difference functions. As a scientific computing library, it should provide common mathematical functions that programmers can easily call or implement. In this example, array 1 has 2 elements, 1 and 100. So what does array 2 equal to? We're using the NP object called the logarithmic function log10, so the result should be 0 and 2. Here we have power, which is an exponential operation. The first parameter we pass to the function is an n-array object. The second is the exponent to be raised, which is 2 in this case, so it is equivalent to a square operation. The returned result is 1 and 4. Let's look at the difference operation. Now by using the function diff, the first parameter passed in is again array 1. The second parameter is n equals 2, which refers to the order of difference. This means that we are going to perform a second-order difference operation, or that the operation will be carried out twice. What does this mean? Well, we intend to obtain the value by subtracting the previous element from the next element. So 3 minus 1 is 2, 4 minus 3 is 1, 5 minus 4 is 1, and 8 minus 5 is 3. That is the first-order difference. Run the same operation on the intermediate data, and we arrive at the final results, which is minus 1, 0, 2. This is what we mean by a second-order difference operation. Let's move on to talk about statistical functions. We first examine the COMSUM method, which calculates a cumulative sum. This is the same idea as a Fibonacci sequence. We have 1, 3, 4, 5 as the original elements here. We put the first element in the first position of the result, and in the second position we have the sum of the first two elements. In our case, 1 plus 3 equals 4. How is the third element of 8 obtained? Well, it is the result of adding the next element 4 to our previous sum. We obtain the last element of 13 in the same manner. This is the COMSUM function. To find the maximum value, we use the Amax function. For the array 1 object, its maximum value is 5. We can also conveniently find the average by calling the mean method and passing the end-array object. We find the result is 3.25. Of course, we can also find the median, quantile, and so on. Now we'll talk about bit operations or bit computing. Bit computing is very commonplace in computer science because of its fast runtime. It gets employed in many scenarios. For example, when we do bitmaps, hash operations, data encryption and decryption, etc., bit operations occur behind the scene. So let's take a look at Numpy's support for bit operations. All such functions in Numpy start with bitwise underscore, and then specify the corresponding operation. For example, bitwise underscore AND performs the AND function to each pair of the same index elements for two AND-array objects. Bitwise underscore OR means that the elements are all read by position. There are also reverse, left underscore shift, and right underscore shift operations. Let's take a look at the figure on the right. We now specify two variables, a and b, which are equal to 2 and 3. We can use the bin function to convert decimal numbers to binary. When we do this, bin A, bin B, and print out the results, we can see 2, 3 in binary is 10 and 11. The prefix 0b is added to indicate that the value is binary. Let's take a look at the bitwise AND operation. After passing in a and b, we print the result. Bitwise AND of 10 and 11 should be 10. So we can see the printed result is 0b, 10 in binary, and 2 in decimal. And that's bitwise AND. Now for bitwise OR, we run bitwise underscore OR AB. The result should be 11. When we print the result, the binary form is 0b, 11, and the decimal value is 3. Those are the bit operations. Let's look at the string operations. Numpy supports several related operations, such as string case conversion, string slicing, segmentation, and so on. Let's look at some of the more commonly used string functions, such as add. Add concatenates elements of two strings position by position. You can understand this as a splicing of strings. Though for ND-array objects, it is actually the splicing of elements in the same position. Lower converts all the object elements to lowercase and upper or to uppercase. Split is to split the string according to the separator. Replace means that we can replace a particular substring with a new value. Let's look at these through some examples. In the first figure on the upper right corner,
we have created an array object array1. There are 3 elements in it, I, like Python, which is all strings. We then call np.char.upper and pass in the object array1, which means that all characters are converted to uppercase. We see that's the case in printed results. Below that, we pass in the entire string, I like Python, to illustrate the string segmentation using the split function. We see that the resulting object has the string broken down into 3 individual words. Finally, we have the replace function. We replace the substring Python with Java, and we get I like Java as the result. So these are some basic string operations supported by Numpy. We finished with the introduction to Numpy, and we'll now take a look at Pandas. First, let's consider some of the basics of the library and the underlying data structure. Pandas primarily provides functions that enable us to quickly and conveniently process structured and large volume data. It is compatible with both Numpy's high-performance array calculation functions, as well as flexible data processing functions of spreadsheets and relational databases. We can directly load Excel files or relational data tables from databases such as MySQL and PostgreSQL. After loading, we can perform data cleansing and pre-processing operations. Let's look at an example. For users in the financial industry, Pandas provides a large number of high-performance time series functions and toolkits well-suited for financial data. We have the knowledge system in the figure on the right. We will mainly cover 3 topics: reading and writing data to disk, data processing, and data manipulation. In terms of data processing capabilities, we can perform variable discretization, missing data processing, and data standardization. Data manipulation capabilities including data slicing, combination, and so on. Let's go into more details. We should first understand the main mathematical model or data structure of Pandas. Pandas have 2 data structures. One is series and the other is data frame. Series is a one-dimensional array, usually used to represent a vector. Data frame can represent a multi-dimensional array. In other words, matrix, tensors, and so on. The installation of Pandas, similar to other Python libraries, is also very convenient. Using pip install Pandas, we can introduce the library to our Python environment. Before using Pandas, we must first import it. In our example, import Pandas as PD, imports the library and then renames it to PD. We now create a one-dimensional array using pd.series. Note that we are passing in a Numpy object as one of the parameters. We previously learned that calling the random method through np.random will create a one-dimensional 5-element array containing random numbers between 0 and 1. We need to specify an index A, B, C, D, E because Pandas needs labels for its columns. With this, we've created a one-dimensional array. Next, we can create a date frame using pd.dateframe. Here we pass in a dictionary structure. D is a standard dict data object in Python with 2 keys 1 and 2 as well as corresponding columns of values. When we print this data structure, it looks like this. For series, the one-dimensional array or vector contains these 5 random numbers. For data frame, we have a 2-dimensional matrix that looks like this. This is how we can create Pandas data structures. Now let's look at methods for creating series and data frame. When we create a series, we can pass in an ND array, a list, or a dictionary object. When creating a data frame, we can pass in a Pandas series object, or the same 3 data types mentioned before. On the right, we have a specific example. It is similar to the one from the previous slide. In the first case, we create a series by passing in a Numpy ND array object, which can be a random number series. In all-one ND array, a dictionary or a list. In the case of a dictionary, we need to specify the labels of the columns. With a list, the default label starts from 0, 1. We get results that look like this. Let's move on to reading data. We can load data through files into data frame objects.
we will look at some commonly used functions. To read in Excel or CSV files, we can use the read CSV or read table methods to load the file data into memory. Read CSV handles the reading of CSV files. In the example on the right, pd.read_CSV. The incoming file is in CSV format, and we specify the file delimiter. Normally a tab is used, but it may also be a delimiter specified by the programmer, such as a comma or a semicolon. This particular file uses a semicolon as the delimiter. Now that we have completed loading the data, let's take a look at some of the data characteristics. WineQuality-red.csv is a public dataset that has several attributes related to wine quality. We often use public datasets such as this to feed into algorithms. In this case, to classify whether the quality of the wine is good or bad, it contains several attributes. After loading the data frame object, let's check the data. We call the head method to view and print the first 5 rows of data. We can see that its structure is like this, which is the same structure as the file. It includes specific values such as the concentration index of the wine, sugar content, etc. We've now loaded the data from the CSV file into memory and converted it to a Pandas data frame object. Next, we often need to perform some operations on the loaded data. Let's look at some of the commonly used parameters for read CSV and read table. First, we have path, which represents the location of the file in the file system. This parameter is of string type. We pass in a specific path so that we know where in the file system to find such a file. Sep represents the delimiter used to separate file columns. Header specifies whether or not the first row of the file is the header, which is often the case. If there is no header in the file, we don't need to load it. Names is a list of column names in the file. Skip rows means that there may be some rows that we don't want to load, which we can use skip rows to ignore. Then there is NA_values. The data that we load often may contain some missing data. How do we deal with this? We often choose to replace the missing data with special values such as NA. This way we can see that the value of a position is missing when doing subsequent data processing. We also have encoding, which denotes the encoding used in the original file. This prevents the data from being gobbled during the data loading process. We need to have consistent data encoding in the loading process. After loading the data, we mainly want to analyze or display its metadata. We need to understand information such as the data count, the attributes of the data, and whether there are missing values. Understanding the raw data is often the first step in performing data analysis or running machine learning algorithms. If we don't have a good sense of the overall data structure or condition, it becomes difficult to select the appropriate algorithm. Let's introduce a few commonly used methods for doing this. See, we want to know whether the data has duplicates. We would use the duplicated function. We use the count method to find out how much data we actually have. To find out which columns are contained in the data, we use the columns attribute. We can see the actual function calls in the upper right corner. After we get the object wine_quality_df, we call the count method to see how many data records it has. We also use columns to see what columns the file contains, as well as duplicated to see whether or not the file contains duplicates. Here are the results which represent the file's metadata. The first part shows the data columns and how many records each contain. 1,599. The last true expression indicates that the file does have duplicate records. We can also see that the file has no missing values since each column has the full 1,599 count, which means no missings, but some duplicates are present. Now let's see how we would write the data back to the file. After loading the data, we run a series of processing operations. We then want to write the results back to the file system. At this time, we would often use the to_CSV method. By default, the row and column labels are included. but we can set the index and header operation to determine whether or not this is done. We often don't need to write back row labels, but writing the header is usually necessary. The parameters of the to_CSV method and the read_CSV methods are basically the same. We need to specify the path in the file system, its character encoding type, header, and so on. In this example, we load the CSV file and then write the first 5 rows back to the file system. The code to do this is in the lower right corner. We first load the wine quality file using read_CSV. SEP indicates that the original file is separated by semicolons. We now get the first 5 rows and call the to_CSV method to write it back to the file out.csv. Here we change the delimiter to \t when writing back the data. When we open the out.csv file, we can see that the row index and column labels were all written out by default. There are 5 rows in total and 7 columns. Let's talk about data discretization now. In the process of data analysis, we often need to discretize continuous attribute values into enumerations of discrete values to facilitate further processing. To do this, we use the Pandas concat function. Let's take a look at the specific example on the right. This process of discretization is also called binning, which is to set data intervals. Here we have the pH value of red wine between 3.0 and 3.7, and we set the interval to be 0.1. We then have bins or segments such as 3.0 to 3.1, 3.1 to 3.2. We use the pd.concat method to create bins for the attribute pH_se, and the result is pH_bins_se. Let's take a look at the results after we run the concat function. This is what it looks like. The original pH value is 3.51. After binning, its discretized bin is between 3.5 and 3.6. Similarly, with 3.20, its bin is between 3.1 and 3.2. 3.26 is between 3.2 and 3.3, and so on. And that's data discretization. Let's see how missing values are handled. Why do we need to deal with missing values in the first place? With large volume data, there are often data irregularities that cause some columns to have missing values. If we do not take them into consideration, the missing data may cause determination of certain subsequent data calculations. In Pandas, missing values in floating point and non-floating point arrays are denoted by floating point value nan, which is short for not a number. This clearly indicates that a value is missing at a particular position. The built-in non type in Python, for example, also gets treated as a missing value. Let's look at the example on the right. We have created a series object, which contains 5 elements, including non, a, np.nan, and c. Let's see which of these will be treated as missing values. We call the isNow method on the Pandas series object string_se to do this. We can see that the Python non is a nan value, so here is true. A is not, so here is false. Nan is also a true. Finally, and C are not considered missing values. We've now finished covering Pandas basics. Let's move on to an overview of Scipy. Scipy is a Python toolkit used in the fields of mathematics, science, and engineering. It can handle integration, interpolation, optimization, image processing, numerical solution of ordinary differential equations, signal processing, etc. In combination with Numpy, we can essentially replicate all the capabilities of MATLAB. It also has some capability with MATLAB by supporting the same input and output formats. Let's take a look at the relationship between the three of Numpy, Pandas, and Scipy. Numpy mainly performs calculations on high-dimensional arrays and basic numerical values. Pandas, due to its sound distributed computing capabilities, is mainly used for structured data processing of high-volume data. Scipy is more focused on complex scientific computing, including toolkits for advanced mathematics, machine learning, and other engineering sciences. We can see each has a different focus. Let's take a look at some Scipy basics. First, note that Scipy supports all Numpy functions. In other words, with the Scipy namespace, we can call all the methods and attributes of Numpy mentioned before. There is a bit of reinventing the wheel here, but Scipy is designed to make everything more complete, though in many respects it's developed based on Numpy to maintain consistent APIs. The same Numpy attributes and methods are again defined with the Scipy namespace. For example, in the figure on the right, we know Numpy's ND-array object has many attributes, including ndim, shape, size, and dtype. In the Scipy namespace, we can call on all of them. Of course, we must first import the Scipy package into the execution environment using import Scipy as sc. Then we use sc to create a Numpy ND-array object, sc.array. Its dimension is 2, and its shape is 2-3. With 2 rows and 3 columns, it has a total of 6 elements, and the element type is int64. So Scipy is based on Numpy but provides some additional functions beyond those already contained in Numpy. We will see this a bit later. To install and import the Scipy toolkit into the Python environment, we would use pip install Scipy and import Scipy. In this example, we can see that it reuses the data model of Numpy's ND-array. We repeatedly emphasized before that when introducing a scientific computing toolkit, we must first understand its data structure or data model. We now know that Numpy's data model is ND-array, Pandas is series and date frame, and Scipy reuses Numpy's ND-array, so its data structure is the same. Let's take a look at the commonly used methods provided by Scipy and the corresponding modules. One is scipy.integrate, which is mainly used as a solver for numerical integration and differential equations. There is also scipy.interpolate, which is a toolkit for data interpolation, and lineag, which is mainly used for linear algebra operations and matrix decomposition. Optimize is a function optimizer or root search algorithm. There's also states that produces probability distributions and has various statistical testing methods. Weave is a tool for accelerating array calculations. Let's first look at numerical integration. When a function cannot be analyzed or integrated, we often turn to numerical integration. And this time, we would use Scipy's integrate module. It contains many numerical integration methods, such as the single integral quad, double integral dBl quad, multiple integrals, Gaussian integral, and so on. Let's look at an example of integral. First, a single integral. We call scipy.integrate.quad, passing in 3 parameters. The first parameter is f, which is the function to be integrated. A and B indicate the upper and lower bounds. In this example, we define the exponential function x squared and call the integration function with bounds 0 and 1. Here's the result. What are their 2 values? The first value is the actual integration result. The second is an error value, which is the error between the integral result and the true value. These errors are often caused by the precision-level computer system used to represent numerical values, but we see that its error value is very small. Let's look at a data interpolation. What is interpolation? It is the process of finding a value between 2 points on a straight line or curve. In the fields of statistics and machine learning, data interpolation is also called data fitting. Given several data points, we want to fit them to a specific function in order to predict the value of an unknown data point. In Scipy, we would use the module scipy.interpolate. This module contains many methods for interpolation, including one-dimensional interpolation inter-PYD, spline interpolation, and so on. The example on the right illustrates one-dimensional data interpolation. First, a set of data is created. 12 numbers between the interval 0 and 4. The function we want to interpolate is a linear function transformed using cos. Let's see how this is done using the interpyd method. When we draw the function with the matplot library, we can see that the 12 data points are fitted to a curve like this, thus completing the interpolation process. If we then provide a new x value, C2.2, we can find the corresponding y value using the fitted curve. This is the process of interpolation, which is easily done by combining the capabilities of these libraries. Scipy also provides methods and functions related to linear algebra. For example, it is very common that we are asked to solve a system of linear equations. On the right, we have the tertiary linear equation systems x plus 2y plus 3z equals 18, etc. How do we solve for the values of x, y, z? Here, we use Scipy's linear algebra module, which contains many linear algebra solvers. For example, to solve linear equations, we use the solve method. For eigenvalues and eigenvectors, we use eig. And for singular value decomposition, we use SVD and so on. Let's look at an example of solving a system of linear equations. To do this, we first import the linear algebra module. A and B are the two parameters. A is 1 to 3, 2, 3, 1, and 1 to 6, which are the variable coefficients on the left side of the equation system. B is the value of each equation on the right side of the system, 18, 6, 3. We pass in A and B to the linearalgebra.solve method and get a solution that looks like this. X is equal to minus 7, 7, Y is equals to minus 5, 5, and Z is equals to minus 5. We've solved this system of equations rather easily. Within this, we've completed the introduction of scientific computing in Python and some of the commonly used libraries. In summary, we first covered the basics of Python scientific computing, including the entire toolkit ecosystem of Numpy, Pandas, Scipy, and Matplotlib. In the interest of time, we did not cover Matplotlib in detail. We did cover the three libraries of Numpy, Pandas, and Scipy, including their respective knowledge systems, basic characteristics, the key being their underlying data structure or data model, as well as the corresponding data operations. For Numpy, we introduced attribute and method creation, indexing methods, mathematical, statistical, bit, and string operations. For Pandas, we covered data loading and writing, as well as data discretization, mean value processing, and so on. For Scipy, we introduced data integration, data interpolation, and solvers for linear algebraic equation systems. With it, we conclude Lesson 12 on Python scientific computing. Thank you all.